And you can go back and forth between exponentials and logarithms. What it means, y is equal to log base a of x if and only if x is equal to a to the y powers. This is the really, really important piece. So essentially what this tells us is that the logarithm is telling you an xy. If I said like log base 2 of 8, it's saying 2 to what power would be 8. So when you're looking at that, we'll talk a lot about the domains of the logs. This number is always going to be a positive, because if you take a positive number to a power, you only get positive answers out. So in a log, the base, which is that a, and the argument, which is the x, both have to be positive numbers. The only place you could see a negative here is in what it is equal to. Everybody have that one? So, for example, I just want to make sure we can write these definitions to start us off. So if I rewrote this in exponential form, you always start with the base. The base of the log and the base of the exponential are the same thing. So my base of the log is 3, so I start there. So it's 3, go across the equal sign to the y power equals x. It just makes a little loop. So how would I write the second one? To the y power equals x. We always just kind of drew those little arrows in. Start with the base. Let's do a couple, and the next few slides, I've got lots of examples. We'll do as many or as few as we need on this. I just wanted to make sure we have that definition. We have to be able to go back and forth between the exponential and the logarithm. So I want to take this and write it using a logarithm. So it would be log, what would my base be? Right, the base of the log is the same as the base of this. Then you go across the equal sign. So log base 1.2 of m equals 3. Make sure your notation is good. The base should look like a subscript. I should be able to clearly tell that this is a small subscript 1.2, this is a regular sized m, so make sure you're using proper notation there. How would I write this one? Log base of equals 8. Okay, so can you guys go back and forth? Do we need more practice with changing the forms? Let's start evaluating some. Word of warning. Your calculator has a log button. Okay? But if you just type that log button and the 16, you will not get the right answer, because the log button you have is log base 10. Now, I always have somebody that loves to play on the calculator. Yes, there is another way to get into a place in the calculator where you can change the base, but that is not worth our time. We need to learn how to evaluate these because pretty soon I'm going to be throwing lots of variables in here, so your calculator will do you no good then. So let's learn how to do these without a calculator. If I say log base 2 of 16, there are two options for how to do this. If you understand what a log means, you might be able to look at this and tell me the answer. A log tells you an exponent. This is like saying 2 to what power equals 16? 4. And you've got your answer. Now let's say you can't just look at it and tell. Then you could set this equal to x. Then we can use our definition. This means 2 to the x power equals 16. Didn't we spend like 2 or 3 days last week solving these kinds of things? We would get a common base. 16 is 2 to the 4th, and you get 4. So you can either turn it into an equation, or you might be able to just look at it and tell your answer. Does anybody know what the answer to B will be? -3. If you can't tell, set it equal to x. 3 to the x power equals 1 over 27. Okay, you would have to go to a common base of 3. So 3 to what power would give you 1 over 27? -3. And you get x equals -3. I want you guys to try a couple of those. So C, 2 to what power equals 1? 0. You can do the definition if you need to, and you get the same thing. And D, 5 to what power equals 25? 2. So again, you might tell, you might have to work it out. You just have to do whatever you need to be able to see the answer. Yes, ma'am.
If we don't work it out, then we just write equals and then number.
Yep. Do we need any more like this? So let's talk about the relationship between the log and the exponential. What we're going to do is graph a log and an exponential and see if we can tell what the relationship is. So if I said to graph y equals 2 to the x. We did that last week. We had a day of graphing. What numbers did we always plug in for x? Okay. 2 to the -1 is 1/2. 2 to the 0 power? 2 to the first, 2. So we plotted those. Remember, it always had a horizontal asymptote at 0. So that is our 2 to the x. Now, if I want to graph y equals log base 2 of x, you might be comfortable making your t-chart from here. Most people are not. So if we rewrote this in exponential form, what that means is 2 to the y power equals x. if you made your t-chart, this is an exponential, but which variable would you be plugging in for? The y, because it's the exponent. So we put in our -1, 0, and 1 for the y. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. So I get 1/2 -1, 1, 0, 2, 1. This time it's going to be the vertical axis that I get closer and closer to. What's the domain of the first one? The blue one, the 2 to the x? What's the range? I see 0, infinity. Okay. For the red one, my log base 2, this one has a domain of 0 to infinity, and my range is so how are these related? They're the opposite. Look, the domain of this one is equal to the range of that one. Those are equal. Look at our order pairs. I took the order pairs and just flipped them. If I drew the line y equals x, just a mirror image across that line. What's the word for this? Inverses. So the logarithm is the inverse of the exponential. It's that thing that undoes the exponential. So what that means then is the domain of the logarithm is equal to the range of the exponential, which we saw from before without transformations was always 0 to infinity. The range of the log is equal to the domain of the exponential, which is negative infinity to positive infinity. The exponential has a horizontal asymptote at 0, so the log has a vertical asymptote at 0. You just flip your x's and y's. Question. So let's do some graphing. So if I asked you to graph f of x equals log base 1/3 of x, we're going to do this a lot like with the exponentials. We always plugged in those 3 points. What I recommend is to go ahead and change it to an exponential first, and then go from there. So your base, this would be like 1/3. F of x is the same as what variable? 1/3 to the y equals x. So in your t-chart, what are you going to be plugging in for, x or y? The y. You're going to put in -1, 0, and 1. So 1/3 to the -1, 1/3 to the 0, and 1/3 to the first. Okay. So we can plot those. We know, just like the exponential always had that horizontal asymptote, this one will have a vertical. So our graph looks something like that. Why don't you guys graph B? It was f of x equals log base 5 of x. Got something like this? What if, I'm going to kind of add this on, since I already have those graphs right there. What if I said f of x equals log base 1/3 of x plus 2? We can graph log base 1/3 of x, right? That's what we did on part A. That's like your parent function. And so you had those points from part A, 3, -1, 1, 0, and 1/3, 1. So if I asked you to graph log base 1/3 of x plus 2, what will that plus 2 do to my graph? Left 2, because it's attached to my x. Okay, when I move this graph left, what is going to happen? I'm moving each point, but I also have to move my asymptote with it. Okay. So my vertical asymptote is now at -2. And our graph looks something like that. So make sure you watch with those transformations. If you're moving left or right, this time it is going to move your vertical asymptote. So why don't you guys draw me a quick graph of log base 5 of x minus 2. function from part A. What's the transformation this time? Down. Because it's not in parentheses, so it's not bothering x. So you just move each one down 2. So since my asymptote is vertical, moving up and down will not move this asymptote. So my graph just looks like that. Could you give domains and ranges on these? This one, domain would be -2 to infinity. Range is always going to be negative infinity to positive infinity. This one, domain would be 0 to infinity. Range, negative infinity to positive infinity. Let me put one up that might be a little bit harder. So I'm using the same parent function again just to save time. We already have the points on log base 5 of x. That's 1/5, -1, 1, 0, 5, 1. Okay. I have a 4 minus x here. You could also think of that as a negative x plus a 4. This one is pretty tricky to try to figure out your transformations. You would then kind of be twofold because we have to move left and right as well as the negative on the x. To actually figure out your transformation, you would have to pull the negative out of that. So then you have to think, what does a negative on the x do? Flips it over the y. And what would that minus 4 do? It's attached to the x, so right 4. So what we're going to end up doing is flipping over the y and moving right 4. Now if I do that, so like this one, if I flipped over the y, it would go here, right 4. Okay, this will go to -1 if we flip over the y, then right 4. This will go to a -5. And then right 4. And so our graph is going to look like this. Where is my asymptote at? 4, because when you move to the right, that moved your vertical asymptote to the right 4. My suggestion, if you struggle with that, you could always make a t-chart. If you rewrote this, it would be 5 to the y power equals 4 minus x. I would probably manipulate this equation to get x by itself. So like you could add your x over, subtract, and then you can make your t-chart, plug into y, and figure out exactly what your x is. So if you get confused with the negatives aimed to left and right, it's a lot to process at once, you can always go back to making a t-chart if you needed to. Okay. Are there any questions? Do we need more graphing problems? So then, let's give you time to work.